And we're back at it, nerds. Today we are going to move on to section 5.4. We skipped over section 5.3 because it was full of stuff that is not state standard and it really wouldn't have helped you at all, and that's why we're just going to breeze on by it. You might be wondering why we didn't finish the last set of notes. That's because the last set of notes with the factoring stuff was just applications of factoring. I mean, it was application of factoring. They were just some area and volume questions, and they clearly weren't in the homework. So if we have time, I would be more than happy to do those questions, especially since I spent so much time making them, especially the first one. But it's more important that we spend our time on the standards. So like I said, we'll move forward, and if I have time, I'd be happy to go back and do those questions. We'll just see what happens. Because of today's shortened period, I don't think I'll have time. I really didn't have time in the first period. We'll just see. I am calling section 5.4 polynomial theorems, and I have to say it like that because there's actually an extra section in the textbook for honor students called section 5.4a because it has a standard in it that is only standard for Algebra 2 honors. But I don't really see a reason to teach a 5.4a and a 5.4. So instead I combined both sections into one lesson and put all three things that you would have learned in one lesson. And those three things are the remainder theorem, the factor theorem, and the rational zeros theorem. And since those are the only three things we would have learned in those two sections, I went ahead and called it polynomial theorems. So if you look in your textbook, that's not what that section's called, but it's because I combined like 1.5 sections into polynomial theorems. And the good news is we've pretty much already done the first two. I just didn't give them official names. I didn't put them in these little official boxes on my notes, but we have discussed them way back in the day. Let me grab this piece of scrap paper that I was doing some trig on a minute ago. Way back in the day when we were talking about polynomial long division and then synthetic division, I started that lesson with a question. I asked what the remainder for this was. And we decided that we had a remainder of 2, right? And we came to the conclusion of why there was a remainder. And the reason why there's a remainder is because 5 is not a factor of 12, if you remember that. That's how we did that. And then we said, basically, anytime we did our synthetic or our long divisions, if we got a remainder, the conclusion was we weren't dividing by a factor. And if we got a remainder of 0, the conclusion was, woohoo, we divided by a factor. That's actually called the factor theorem. So we already learned that one. And the remainder theorem is really easy. It's really cool too. It says, if you're dividing a polynomial by some linear term, which means you could have done long or synthetic division, if you're dividing by some linear term, x minus k, and it doesn't matter what k equals, you could have found the remainder of the division without doing the division. All you would have had to have done was plug k into f of x. Where's that scrap paper? Do I have room on here to show you more stuff? I'm going to squeeze some stuff on here. You don't need to write any of this down, but I'm just going to show you. Let's grab a random polynomial. Something that I know you can factor by hand. This easily factors by hand. Okay? Its two factors are x plus 3 and x minus 1. And those are its only two factors. That means if I divide f of x by any other linear term, I'm going to get a remainder. And I could either do the synthetic division, the long division, or I could use the remainder theorem. Let me show you what the result of the synthetic division would have been. It's because it's good review. So I don't want to do the long division. Let's do the synthetic division. The synthetic division says take the 0 of the divisor. Make sure you're not missing any terms. 2, 1, none. I'm not. So 1, 2, negative 3. Negative 2 times 1 is negative 2. 2 plus negative 2 is 0. 0, negative 3. You can see that if I had divided this quadratic by this linear term, I would have gotten the remainder negative 3, right? The remainder theorem says, instead of doing all that work, we could have just done this. We could have just plugged negative 2 in instead of doing this synthetic division. Negative 2 squared is 4. 2 times negative 2 is negative 4. 4 minus 4 is 0. And 0 minus 3 is negative 3. See, the remainder theorem got us the remainder of negative 3, bypassing any synthetic or long division. The remainder theorem would not give us the resulting polynomial, but it would give us a remainder. So what we do is we use the remainder theorem as a shortcut to figure out if we're dealing with a factor of our polynomial or not. Because if the remainder was 0, you found yourself a factor. So in tandem, these two things give us a shortcut to figuring out if we're dealing with a factor of our polynomial or not. That's what they do. So here I have another quadratic. f of x is 3x squared plus 7x minus 20. We're going to divide by this, this, and this to find the remainder. Ew, but you know what? Instead of doing the actual division, we'll just use the remainder theorem. And the remainder theorem says, I don't need to divide by x minus 2. I can just plug in 2. I don't need to divide by x plus 1. I can just plug in negative 1. And I don't need to divide by x plus 4. I could just plug in negative 4. And remember, all that's going to do is get me a remainder. That's all that will do. But the remainder can help us draw some conclusions. So let's do it. Let's start with purple. A. The remainder, if we had divided by x minus 2, is the same thing as if we simply evaluate using the 0 of the divisor. 2. So let's plug in x equals 2 and see what we get. 3 times 2 squared plus 7 times 2 minus 20. Okay, 2 squared is 4. 3 times 4 is 12. 7 times 2 is 14. 12 plus 14 is 26. 26 minus 20 is 6. Here's what we know. If I divide this quadratic by this linear term, this is my remainder. And anytime you have a remainder that is not 0, you have found something that is not a factor of f of x. So the conclusion is x minus 2 is not a factor of f of x. So you might be wondering why you care. Well, remember I told you this whole chapter is about factoring polynomials so that in the long run you have the ability to graph these polynomials. We now know that my graph does not cross the x-axis at positive 2. That's cheating a little bit. I'm giving you a little bit of further knowledge, but that's what's up. What's a good color to go next? How about green? Part B. Instead of doing the synthetic or the long division, f of x divided by x plus 1, I could find the remainder simply by evaluating f of x using the 0 of the divisor, so negative 1, the same exact number that I would have used if I was doing the synthetic division, and plug it in. Let's see what I get. 3, negative 1 squared, 7 times negative 1 minus 20. Negative 1 squared is 1, so that's just 3 times 1. 7 times negative 1. See, 7 and 20 makes 27. 3 minus 27 is negative 24. Another remainder that does not equal 0. Conclusion? X plus 1 is not a factor of f of x because I got a remainder that's not 0. I'm hunting for remainders that are 0 so that I can claim something is a factor. Last one. Let's see what happens if we divide by x plus 4. Okay, I don't want to actually do the division. I'll just figure out what the remainder of the division would have been. So I'll evaluate f of x using the divisors 0. So I got to plug in negative 4. All right, number is getting a little bit bigger on us, but it's no big deal. You'd be allowed to use a calculator. See, negative 4 squared is 16. 3 times 16 is 48. 7 times negative 4 is negative 28. 48 minus 28 is 20, and 20 minus 20 is 0. The remainder is 0. There is no remainder when I do the division. Since there's no remainder when I do the division, I am guaranteed that x plus 4 is a factor of f of x. And since I know one of the two factors, I could easily find the other factor if I needed to. I mean, we know that I'm trying to get to 3x squared plus 7x minus 20, right? Here's what we know. One of the two factors is x plus 4. You know the two front numbers have to multiply to be a 3x squared, right? So then what has to be here? 3x. And you know the two back numbers have to multiply to be a negative 20. So what's here? Negative 5. There, it's factored. No Lizzie method, no factor by grouping. We were able to factor it because we knew one of the factors. Wasn't that convenient? So if you know one of the factors, finding the rest of the factors of a polynomial becomes much easier. What do you think about that? Can you handle that? Yeah? Here is a third-degree polynomial. It's got 4 terms. As of right now, the only method you have for factoring something with 4 terms is grouping, right? If I said to factor this, you would try grouping. And you would see that the first group has an x squared, and it would leave you a 2x minus 3. The second group has a negative 1. But it would not leave a 2x minus 3. And since they wouldn't leave the same set of parentheses when you pulled their GCFs, factoring by grouping fails. So this polynomial cannot be factored by grouping. But that doesn't mean it doesn't factor. It just means you need more tools. Well, I'm going to tell you one of the factors is x minus 2. And we're going to use that knowledge in a moment to find the rest of the factors. First, we have to show that x minus 2 actually works. Cool? So I want you to do the remainder theorem to show that x minus 2 is a factor. Basically, when we plug in x equals 2, we had better get a remainder of 0. So the remainder, had we evaluated our polynomial at the 0 of the divisor, which would be plugging in positive 2, had better be 0. Let's see. So 3 squared is 16. Excuse me, 3 squared is 8, and 2 times 8 is 16. 2 squared is 4. 3 times 4 is 12. So I've got this minus 12. Negative 5 times 2 is negative 10, and then plus 6. Okay, well, 16 minus 12 is 4, and 4 plus 6 is positive 10. 10 minus 10 is 0. Because we have a remainder of 0, we have demonstrated that x minus 2 is definitely a factor of this polynomial. And because we know that the remainder is going to be 0, it is worth our time to actually do the synthetic division and figure out what the remaining factors will be. Let us do the synthetic division. Let's make sure we're not missing any terms. X to the 3, 2, 1, none. We're not missing any terms. That's good. No gap teeth in this one. Remember, the synthetic division uses the 0 of the divisor. Only the coefficients. 2, negative 3, negative 5, and then 6. Remember, if there was a term missing, you would have held that term open with a 0. Okay? And we already know at the end of our synthetic division that our remainder will be 0. We just showed that. Writing this plus sign and drawing this arrow are never required. I'm only doing it to remind you how synthetic division works. Two times 2 gets us 4. Adding straight down, negative 3 plus 4 is 1. 2 times 1 is 2. Negative 5 plus 2, that gets me my negative 3. And 2 times negative 3 does get me the negative 6 that would be required to get a 0 here. Great. The original polynomial was a cubic. I divided by a linear. Anytime you divide an x to the third by an x, what will your result be? Anybody, please save me. One more time. This is the whole class full of people not paying attention. Anytime you divide a cubic by a linear, an x to the third by an x to the first, what will the result be? An x squared. That means this is a quadratic. It is 2x squared plus 1x minus 3. And our instructions were to find the remaining factors of the polynomial. We already know one of them. We already know this. So far, our f of x can be written as x minus 2 times this. But we're not finished factoring because this quadratic factors. There are several methods for factoring. You could do the whole Lizzie method setup if you can remember how the Lizzie method works. You could do what I did with you earlier in the year where you say 2 times negative 3 is negative 6. The two numbers that multiply to negative 6 and add to 1 are 3 and negative 2. So you could write this as 3x minus 2x. Then you could factor by grouping. However you know how to factor, you use that method. I've taught it more than once this year. You learned it in Algebra 1. I'm not teaching that anymore. You know how. So I'm just going to factor it real quick. There. That's how it factors. How did I do that? I used a very fast method of guess and check in my head. I knew that the two ending numbers had to multiply to a negative 3. So I knew one was a 1 and one was a 3. I knew one was a plus and one was a minus, and I just checked between the options real fast. I knew I had to get a positive 1 here. So I knew this couldn't say minus 3, because that would have gotten me minus 6. I knew it couldn't say plus 1, because that would have gotten me 2 minus 3, which is negative. So I just went through the options real fast in my head. But this is the full factorization of your polynomial. So given one of the factors, you were able to find the other two, when originally you couldn't factor this by grouping. But did you notice that the only reason why you were able to factor this is because I gave you one of the factors? What if I hadn't given you one of the factors? Then what? That's what you should be wondering. Let's do another one. One that I had fun creating. Massive 6th degree polynomial. Once again, I'm going to give you one of the factors. I'm telling you that x plus 1 is one of the factors. We're going to use that knowledge to find the rest of the factors. But first, we have to show that x plus 1 actually is one of the factors. We have to prove it works. So use the remainder theorem again. As long as I get a remainder of 0, then I know it's one of the factors. I'll plug in negative 1 because that's the 0 of the divisor. It doesn't take a long time to write out. Got a lot of terms. And I'm trying not to write too large because there's this pesky hole in my paper right here. So I need to be able to squeeze all the numbers into this space. See what we get. Negative 1 to an even power is positive 1. Negative 1 to an odd power is negative 1. So far I have 0. Negative 1 to an even power is positive 1. And negative 4 times positive 1. So that's just going to give me minus 4. Negative 1 to an odd power is negative 1. So negative 5 and negative 1 is positive 5. Negative 1 squared is 1. Oh, but minus. 4 times negative 1. And then plus 4. This darn hole in my paper. Well, let's see. 1 minus 1 is 0. 0 minus 4 is negative 4. Negative 4 plus 5 is 1. 1 minus 1 is 0. And negative 4 plus 4 is also 0. So yes, it works. And if that hole hadn't been there, I'd have been able to write equals 0 and squeezed it in. Shucks, shoot, darn. The point is, the remainder theorem showed us that, yeah, x plus 1 is one of my factors. I now know that my polynomial can be written as x plus 1 times some other stuff, right? And specifically, if I'm dividing a 6th degree by a 1st degree, what will I get? A 5th degree. A 6th divided by a 1st gets me a 5th. So here's what I know so far. I already know that I've got this x plus 1 times, and then the next thing is going to start with an x to the 5th. And there's going to be some other crap after it. That's what I know right now. But let's see what all that other crap is and see what we can do with it. Synthetic division to the rescue. And also, make sure you don't have any gaps in the polynomial. X to the 6, 5, 4, 3, 2, 1, none, no gaps. Remember, if you have a gap, you have to hold that position open with a 0. So my numbers are going to be 1, 1, using the coefficients here, negative 4, negative 5, negative 1, 4, 4. And we already know that the remainder is 0. We just demonstrated that with the remainder theorem. The plus sign and the arrow are never required. I'm only doing it for good notes. Okay. -1 times 1 is -1. 1 plus -1 is 0. Oh, interesting. There is no x to the fourth term. We've already said we know we're going to have an x to the fifth, but there's no x to the fourth. How about that? -1 times 0 is 0. -4 plus 0 is -4. -1 times -4 is +4. -5 plus 4 is -1. -1 times -1 is +1. And oh look, another 0. -1 times 0 is 0. Adding straight down gets me my 4. -1 times 4 does get me the -4 that was required to get the remainder of 0. Cool. So what we have here are the coefficients of our 5th degree polynomial that we know was going to be the result of dividing a 6th degree by a 1st degree. These are our coefficients of our 5th degree polynomial. So right now we have x to the 5th plus no x to the 4ths minus 4x to the 3rd minus x squared plus no x's plus 4. That's what's left over. That's what is up here right now, okay? The instructions, just like the last question, were to find the remaining factors. That means we must be able to factor this. It has 4 terms, and you have one tool for factoring 4 terms. Grouping! Let's see what happens when we group. So now we get to practice yesterday's stuff. What's the GCF of this first green group? X to the 3rd. Yeah. See what's left. X squared minus 4. And, well, they don't really have not much in common at all. What's the GCF of the second green group? -1, because remember, anytime you're trying to factor something that begins with a negative term, you have a negative GCF, and that leaves behind the x squared minus 4. That makes the x squared minus 4 my new GCF. I could factor an x squared minus 4 from both big green objects. And when I do, the green objects that are left behind are x to the 3rd minus 1, and oh my goodness, a special case and a special case. How about that? This one is a squared minus b squared. Where hopefully you can see that a is x and b is 2. Get short, math. Get squeezed in. And this is the difference of 2 cubes. I hope that you have memorized your formulas. It helps if you write them every single time. Where a must have been x and b must be a 1. We are ready to write this thing in its fully factored form. That's a lot of F's. Like my grade book. Okay, like 2 people chuckled. That's funny. There's not a lot of F's in my grade book. But still, it's funny. All right, let's see. Remember, we already know that x plus 1 is part of our factorization because it was given to us. So we know that one of the factors is x plus 1. We might as well write it first. In first period, I had a lot of people confused as to where this x plus 1 came from. It's right there. We were told it's one of the factors. And we used that knowledge to get down here to the black and green. The black and green are both special cases. They both factor. I'm going to write it all in blue, but a plus b, so that's x plus 2. A minus b, x minus 2. Now to the green. A minus b, x minus 1. Uh-oh. Think skinny thoughts, math. I should have written this just a little bit to the left. A squared plus x times 1 plus 1 squared. And there it is. Because this is a true x squared quadratic, that is a result of the difference of cubes. This will not factor, so we don't have to worry. This is the full factorization of our function. So once again, if I hadn't given you one of those factors, you would have been stumped. Yes, ma'am.
What about the GCF?
The x to the third, this GCF?
Yeah.
That's right here.
Okay.
So these two green ones are here, which then got me, you know what I could do? I could underline it. This was the green stuff, and this was the black stuff, like that. And the x plus 1 at the beginning is that. And just so you know, the order of multiplication doesn't matter. So these parentheses could be shuffled around in any order, and you haven't changed the answer. Okay? Just so you know. It's a big question. Questions, comments, concerns about that? Anybody want to ask me anything about that or no? No? Easy peasy lemon squeezy? Yes, ma'am. Mm-hmm. This right here? Yeah, it's when I was plugging in -1. What about it? So the synthetic vision here, these blue numbers are the coefficients of this polynomial, whereas these purple numbers are what I was getting when I plugged in the number -1. Why did I get these numbers here? Because I just plugged in -1 everywhere where I had an x, and just figured out what it equals. Whereas here, these blue numbers are the numbers that sit in front of these x's. These are just the coefficients. They're this 1 here, this 1 here, this -4, this -5, this -1, this 4, and this 4. But in purple, what I was doing was evaluating. I was actually replacing x with a known number. I was saying, what if we let x be -1? And let's see what we get as a result. Like, what would the y value have been on the graph? If I knew x was -1, what would y have equaled? So we plugged in -1 for every one of the x's. And look, all those coefficients were still there, right? There's a 1 here, a 1 here, -4, -5, -1, 4, and +4. All those coefficients are still there. But what I'm doing is replacing x with -1 and seeing what it equals. Synthetic division is a completely separate idea. This was this whole stuff in purple here was done to show us that the synthetic division was even worth trying. Because if this had not equaled 0, we wouldn't have bothered doing the synthetic division. The whole point of doing the synthetic division was because we knew there would be no remainder. Which means that what I got afterwards is how I could finish factoring. Okay, so these numbers don't match these numbers because they're not the same. These are the coefficients. These are what you get when you plug in a known x. Okay, they're only similar because I used a 1. If I had used a 2, they'd have been completely different numbers. Okay, did a hand just come up over here a second ago? No, thought I saw it on my periphery. All right. Then let's move on to the rational zeros theorem. There's a lot of stuff going on in this box. There's a lot of stuff going on. Let me just explain to you what it means in regular people words. When we factor things, there are only certain, let's call them pretty numbers, that are even possible to be factors. Let me come back to this one on the front. Remember when I said I knew that the two front things had to multiply to get me a 3x squared? So we knew that one was a 1 and one was a 3. And I said the two back numbers had to multiply to get me a negative 20. Once I knew one was a 4, it forced the other one to be a negative 5, right? So my zeros, my answers would have been negative 4 and positive 5/3. These numbers were basically dictated by these numbers, here and here. As it turns out, the only pretty zeros, that's what rational means fraction or whole numbers, means no radicals, no imaginaries. The only pretty zeros that are even possible are going to be dictated by the factors of this divided by the factors of the 2 on the front. We call it the P over Q test, basically, where P is all of the factors of the number at the end, positive or negative, and Q is all of the factors of the number on the front, positive or negative. Okay? Now I'm going to finish these notes, and when I finish these notes, we'll get to the mental health stuff, because it's more important to me that we get the notes finished. Okay. So, right now what we're doing is we're finding the possible zeros. That doesn't mean any of them actually even work. These are just the only possible pretty answers. And it's actually very easy to do. We're going to find all the factors of P and all the factors of Q. And then we'll find the combinations. So what is the very first number you know of that can go into 6? 1 goes in. And you could say plus or minus 1. What's the next number that we know goes into 6? 2. So you could say plus or minus 2. What's the next number that you can divide into 6? 3. So either plus or minus 3. And then lastly, 6, positive or negative. Now, because I've said plus or minus on the top, I don't need to say plus or minus on the bottom. That's redundant. You can if you'd like to. It won't make a difference, but we don't need to. So what's the very first number you know you can divide 2 by? 1. And what's the only other number you can divide 2 by? 2. So here are the possible rational zeros. These are the only ones that are even possible. So first, all of those numbers divided by 1. So that gives us plus or minus 1 divided by 1. Plus or minus 2 divided by 1. Plus or minus 3 divided by 1. Plus or minus 6 divided by 1. Then, plus or minus 1 divided by 2. Let's see. Plus or minus 2 over 2. That's plus or minus 1. We've already written that one. We don't need to write it again. Next, plus or minus 3 over 2. And lastly, plus or minus 6 over 2, but that's plus or minus 3, which we've already written, so we don't need to write it again. This is what this tells us. If our graph crosses the x-axis at a pretty place, It must be one of these numbers. It couldn't be anything else. Does it guarantee one of these numbers? No, it does not. But what it tells us is, if that graph crosses at a pretty place, it's one of these. So we now know it's impossible that the graph crosses at x equals 5, because it's not on this list. So basically, this rational zeros theorem gives us the numbers that we could attempt using the remainder theorem to see what's even worth doing synthetic division with. This gives us our suspects. That's the point of that. So you'll see that go into action tomorrow. Thank you, nerds.